something involving chemistry, equations, balancing equations, ways to classify reactions. And I think this is sort of where we laid up, if I'm not mistaken. So we're going to talk now about sort of molar mass, Avogadro's number, and some sort of calculations that you could do using the equation, which is referred to as stoichiometry. So we'll get into it here. First off, we're going to talk about the mole, and the mole, and the abbreviation for the mole, not the furry guy, but is MOL. They had to cut something off, so they cut the E off, it looks like. And when you do see mole, MOL, that is the abbreviation for a mole. It is not the abbreviation for molecules, which is commonly mistaken. People see MOL and they think molecules, but that is, again, the abbreviation for a mole. So much like in life, we have a lot of words that sort of represent a certain amount of something. So if we say we have a pair of something, that's like 2, right? If we got a dozen, that's 12. If we got a gross, if you count pencils, that's 144. Or paper, I guess, sometimes used to come in grosses. But when we talk about a mole, it represents as much elementary substances as there are in the carbon-12 isotope. If you remember, the carbon-12 isotope is the isotope that they chose to basically figure out the atomic mass of all the elements there on the periodic table. And the mole actually does represent a certain amount of something. So when you say you have 1 mole of something, that equals 6.022 times 10 to the 23. And these could be atoms if we're talking about atoms. They could be particles if we're talking about particles. They could be pizzas if we're happen to order some pizzas, or shoes if we lost our shoes. Perhaps not too much pizza or shoes here in chemistry, but atoms and particles, and probably a better one as well would be molecules is used as well as units. And this number here is what is referred to as Avogadro's number. So Avogadro's number is basically what a mole represents in terms of sort of a numerical value, if you will. And it's always 6.022 times 10 to the 23. We really do use Avogadro's number really as a conversion factor to convert between certain units, and those units, come back to that picture. Those units are really between moles and atoms, or molecules is typically what we use it for. So whenever you have units of moles and you want to go to either atoms or molecules, or even backwards, if you start with atoms or molecules, you would want to go back to moles. You use Avogadro's number basically as a conversion factor. So if you started with moles and you wanted atoms or molecules, you would put Avogadro's number up on top and you would multiply by Avogadro's number, and that would give you atoms per mole. The moles here would cancel and it would leave you with atoms. If you want, if you have atoms or molecules you're starting with, you would actually divide by Avogadro's number. So you put Avogadro's number there on the bottom, opposite, so that they cancel. Our atoms will cancel and will leave you moles. So it really is a conversion factor to go between those two units. And sometimes people want to use Avogadro's number in every single calculation because, well, it's like a number and I feel like I should use it. But you shouldn't use it in every single calculation. You really should only use it if you have a number that's already in atoms or molecules or particles or something like that, or you're asked to solve for a number that's going to be in atoms, molecules, or particles. Otherwise, if there's kind of no mention of any of that stuff, then you really should leave Avogadro's number on the side there and not really use it. Most people, when they use it incorrectly, at least do it good incorrectly. They divide by it, then multiply by it, so it cancels each other out. But if you do it incorrectly, that will not work. So you definitely don't need to use Avogadro's number every time. It just got to be those kind of keywords is what you're looking for, either atoms or molecules, and some type of conversion between them. The relationship between Avogadro's number and stuff is, for example, 1 mole here, other way here again. 1 mole of, say, hydrogen is equal to 6.022 times 10 to the 23 atoms of hydrogen. You can write 2 conversion factors for it, 1 mole over Avogadro's number. Or you could do it the opposite way around, use Avogadro's number up on top. You also can relate it to things that are not atoms, but things that are molecules. So for example, if I had 1 mole of water, which is a molecule, that would be 6.022 times 10 to the 23 molecules of water. And once again, you can write the same type of conversion factors, 1 mole of water over Avogadro's number, the molecules are Avogadro's number up on top over a mole of water. So you could relate Avogadro's number to pretty much anything, molecules, atoms by themselves, along the way there. Any questions on that there? All right, so let's take a look here. So as I mentioned, Avogadro's number relates to an actual numerical value for what moles represent. And another really important sort of conversion factor that we come across a lot is molar mass. And molar mass has the units of grams per mole. So it has both of those units together. The number always stays with the grams part, and it's always like 1 mole for the molar mass. The molar mass is basically the exact same thing, numerically speaking, as the atomic mass of an element. So the number that we see on the bottom of the periodic table there underneath the symbol, this is the atomic mass, which basically, if we pull it off, is 1.008 AMU per atom. Numerically speaking, we could turn this into the molar mass by using really the same numbers. It is numerically the same, 1.008 grams per mole. And once again, the number stays with the grams, and it's always 1 mole. So we could get the molar mass of an atom, we could get the molar mass of a molecule by basically adding up all the parts from the periodic table. Typically speaking, when we go to the periodic table and sort of pull the number on the bottom there, 4 significant figures is typically how many numbers we take off. Depending on your periodic table, you may have a bunch of numbers there, you may have a little less numbers, but the typical sort of rule is you pull up about 4 significant figures. If we look at the atomic mass of sodium is 2299, copper is 6355. So we also can use molar mass as a conversion factor, and really molar mass is our conversion factor to go from grams to moles, or backwards, moles to grams. So that is a conversion you use a lot in chemistry, especially the grams to moles sort of conversion. And where we get really the conversion factor from is, again, just the periodic table. So once again, you could take the molar mass here of hydrogen, and you can really turn it into 2 conversion factors, 1.008 grams per mole. Or again, you could have the moles up on top and 1.008 grams on the bottom. So if we had 5 grams of hydrogen and we want to know how many moles that would be, we would use the molar mass from the periodic table and just do a dimensional analysis opposite move here. So grams are on top, so we do need grams on the bottom. And if we did that there, that would get us 5 divided by 1.008. About maybe a bad example there. I'll go 1 more 0 there, so I'll take it to another sig fig, 4.96 moles of hydrogen in this case. So molar mass is your conversion factor to go from grams to moles, moles to grams. And again, if you are starting with grams, you're going to go to the periodic table and you're going to divide by the molar mass. And again, the grams will cancel and that will leave you moles. If you're starting with moles, you will go to the periodic table and you will multiply by the molar mass, and that will get you grams. So again, that is basically the two sort of conversion factors that you use. So really Avogadro's number and really molar mass is kind of nothing more than really a conversion factor to allow you to go between these units. And again, in the molar mass case, we get it from the periodic table is where we kind of get all those numbers from. And then Avogadro's number obviously is just a number that it is that number. Any questions on that there? So some relationships of how this works, for example, we have 1 mole of hydrogen is equal to 6.022 times 10 to the 23 atoms of hydrogen. 1 mole of hydrogen would also equal 1.008 grams. So those are the relationships of those two. Just like we did before, if you took something like water, 1 mole of water will equal 6.022 times 10 to the 23 molecules of water. Now for the molar mass of something like water, basically what we do is we just go to the periodic table and add up all the parts. So we would go to the periodic table and we would find our hydrogen, that's 1.008. We'd also go to periodic table and find our oxygen, which is about 16. And to find the molar mass of something like water, we basically just add up all those parts. So that would be 2 hydrogens, each at 1.008 grams per mole from the periodic table, plus 1 oxygen at 16 grams per mole. Adding that together gets you 18.02 grams per mole, which would be the molar mass of water. We again could use that as a conversion factor with the 1802 grams on top, the 1 mole on the bottom, or flip it around where the 1 mole is on top and the 18.02 grams is on the bottom. So 1 mole of water would equal 18.02 grams. Any questions on that there? And again, you can do it, as you can see here, from any element. And again, if you're doing the molar mass for a compound or something like that, all you simply have to do is add up all the parts from the periodic table. And again, that will always give you how many grams there are per 1 mole. So whenever you do the molar mass for something, it is based only on the actual formula itself. And what I mean by that is, let's just say we had an equation and you had a coefficient of a 2 in front of it or something in the balanced equation, and you still wanted the molar mass here of water, even though there is a 2 in the equation in front of it, the molar mass is based only on the formula. So you should only do it on the formula. And that's why it's considered how many grams per 1 mole, because it's based on just one of the formulas, basically. Yeah. So sometimes people want to incorporate like the coefficients in an equation into the molar mass. And then when you do something like stoichiometry, which we're going to talk about next, you will be doing that step twice and you'll get the wrong answer. So molar mass, simply take the formula, regardless if there's a coefficient in front of it in an equation. You just take the formula, add up all the parts from the periodic table, and that will give you the proper molar mass for that particular compound. Any questions on that there? All right, so as I mentioned before, we will use these really as conversion factors to go from one to sort of unit to the next. And you should sort of think of it like dimensional analysis when having the units cancel out and, you know, keeping the grams, the number with the grams part in 1 mole. And obviously Avogadro's number goes with the atoms or the molecules part, and that's also per 1 mole as well. Let's take a look at maybe some examples here. All right, so why don't you try a couple of these here. How many moles of helium are there? And 5.46 grams of helium. Go to periodic table. I think helium is 4.003. And how many grams of there and our 0.256 moles of zinc? I'm going to go off the top of my head here and go with 6539, depending on when your periodic table was made. All right, take a couple minutes, see what you come up with here. Okay, let's take a look. So in this case, we're looking for moles and we are starting with grams. So the first question is, do I need to use Avogadro's number here? The answer is I do not. So there's no mention of atoms, there's no mention of molecules or anything like that. So we do not need Avogadro's number. This is really a grams to mole conversion, which means it's the molar mass that we need, and that is from the periodic table. So we would go to the periodic table, and we would find helium, we would see that number. That number would represent that there are 4.003 grams per mole of helium. Or again, we could flip it around and go a mole of helium is 4.003 grams. So we're going to start with our 5.46 grams of helium. Remember, we want to go opposite so they cancel, which means we do want grams of helium actually on the bottom. So we would use the conversion factor like that. We would go moles of helium up on top. 4.003 grams of helium on the bottom. The grams of helium will cancel. We're basically dividing 5.46 divided by 4.003. Gonna get us a 1.36 moles of helium. Any questions on that calculation? Yeah. Now, sig fig wise, really the original number is pretty much where the sig figs would come from. This is sort of an exact number, so you just look at that original number. Looking at the second one here, we got grams of zinc, and we're looking for grams of zinc, and we have moles. So remember, MOL is moles, not molecules. So once again, there's no atoms, there's no molecules mentioned, so we do not need Avogadro's number here. It is the same sort of conversion as we were doing in the first one, which is basically here, moles to grams. Once again, we would go to the periodic table, find zinc, which is what we're interested in. And again, we could get our two conversion factors from zinc, 6539 grams per mole, or a mole is 65.39 grams. Starting with the number that they gave us, we would take 0.256 moles of zinc. Once again, opposites cancel, so moles are up on top. So we do want the moles on the bottom, so we would use the molar mass like that. We're 65.39 grams per mole of zinc. That's going to allow the moles of zinc to cancel, going to leave us with grams, which is good, and also going to leave us with a 0.256. It gives us 16.7 grams of zinc in this case. Questions on those two calculations? So again, you can think of it really as just a conversion, and again, going to the periodic table here, using the molar mass as a conversion factor. Yeah. Which part there? The how math wise I got 16? Is that what you're asking? Yeah. So this is basically just like a conversion factor dimensional analysis we were doing. Okay, coming back and dividing by what's on the bottom. So we basically took 0.256 times 65.39. Same thing here. Basically, this is on top, so we would multiply basically 5.46 times 1, and then come back and divide by what's on the bottom, which was this guy, which is 4.003. So it's the same thing that we did with dimensional analysis. Basically, when you're doing sort of a dimensional analysis like this, if whatever's on top and you have a number on the bottom and say a number up on top or whatever it may be, you're basically going to multiply everything that's on top, however many you got going on there. And then you're going to come back and basically divide by whatever is on the bottom. So that's the process there. Yeah. Other questions? Okay, let's try a couple more here. Let's try gold. What is the mass in grams of one gold atom? And if we have a periodic table, gold is 197, looks like. All right, so take a moment here and see what you come up with. All right, let's take a look. We are looking for the mass in grams, so we ultimately want to end up in grams. We have one gold atom. There's a keyword atom, which means I need to use Avogadro's number, right? So again, we see the atom. What we know about Avogadro's number is 1 mole of it, right, is equal to 6.022 times 10 to the 23 atoms. That would mean that we could get to moles, and that's close to what we need, but we actually need to go one more step right after that. We need to go from moles to grams, and that's going to need the molar mass that we've been using here in the last couple of problems. So in this problem, we actually need to kind of go pathway here, atoms to moles, and then moles to grams. Once again, here, Avogadro's number to do the first move and the molar mass there to do the second move. So we'll start with the first move there, which is our 1 gold atom. Once again, here, we're going to do opposites to get rid of it. So we do need to put atoms on the bottom, which would be Avogadro's number. So that's going to be 6.022 times 10 to the 23 atoms per mole of gold. If I stop the calculation right at this point, the gold atoms will cancel each other out, and I will be left with moles of gold at this point, which again kind of gets me to this step. So we do need to do the next step here. That next step is the molar mass, which would come from the periodic table. So we could pull the number off the periodic table. And really that means that there's 197 grams per mole of gold. Or if you want it the other way around, a mole of gold is 197 grams of gold in this case. So you can use it as the two sort of conversion factors. In this case, remember again, opposites are going to cancel. So we see our moles of gold sitting up on top, which means we do need the moles to be on the bottom. So we will put the 197 grams per mole of gold. That is going to cancel out our moles of gold, leaving us just grams. So in this case, once again, math-wise, we're going to be multiplying everybody up on top, hitting equals, coming back and dividing by everybody on the bottom, and hitting equals in between. And if we do that, we do also want to make sure we use our exponent button. That's essentially 197 up on top, divided by 6.022 to the 23 with our exponent button. Gives us 3.271 times 10 to the minus 22 grams of gold. That is a large number or a small number? It's a really small number. It's like 22 places to the left with a bunch of zeros, right? So we're talking about the mass of just 1 gold atom. You obviously could have got a number after the first step if you wanted to, and then continued on with the calculation. That's perfectly fine, obviously, as well. Any questions on that there? You're curious about the sig figs here. It's really because 1 gold atom would be something you would count and consider an exact number, so you could put as many sig figs as you want on that particular answer. Any questions on that one there? Yeah. It wouldn't be wrong in this particular case because technically 1 gold atom would be like if you had 1 donut on the desk or something. It would be something technically you would count. And remember, exact numbers could technically have as many significant figures as you want. I went to 4 because molar mass was to 4 sig figs, but in this case, actually, you'd be okay on any sig figs in this case, just because it's sort of just an exact number type of. Other questions? All right, let's try a couple more here just to make sure. Let's go with. Let's say we had 32.5 grams of C2H6O, well, ethanol maybe. Let's go with how many moles would that be? And also let's go with how many molecules that would be. And then let's also do, let's do 125. Actually, no, let's do this. Let's do 45.5 moles of NH3. How many grams would that be? All right, so some numbers from the periodic table, which might be helpful. Carbon, 12.01. Hydrogen, 1.008. Oxygen, 16. And our good friend nitrogen, 1401. All right. Take a couple minutes, see what you come up with here. I will as well, since I made it up. I'll hopefully get the same answer, I hope. Okay, let's see how you're progressing. So we'll start with the first one here. And we got grams given to us. We do want moles. So once again, that is our molar mass that's going to allow us to do that conversion. We also want molecules at the end, and that is, again, the key word there. That means we need to use Avogadro's number to get to the very end there. So we'll start with the molar mass part to do the first part of the conversion. So again, we're just going to go to the periodic table and add up all the parts. So for C2H6 and O, there are 2 carbons, each at 12.01 grams per mole. We then have 6 hydrogens, each at 1.008 grams per mole from the periodic table. And again, here we have a 16 for the oxygen on the periodic table. We do all that good stuff there. Looks like a 46.07 grams per mole. Again, that is the molar mass. The grams stay with the number, and it's 1 mole. We could use that again as a conversion factor. So that's the first part of the calculation here. We're going to take 32.5 grams of C2H6O. So using our molar mass as a conversion factor, again, we want to go opposite of where grams are. So they're up on top. So we do need to put the 46.07 grams on the bottom, and that would represent 1 mole of our ethane here. That again comes from the periodic table, and using that as a conversion factor. That will get rid of the grams at this point, and since we do want an answer, we'll get that answer, which would be 32.5 divided by 4607, since it's on the bottom. Probably will help to push the right number. Try that there. And that looks like it will give us something like 0.705 moles of C2H6O here for the first answer. Any questions on where the numbers came from or anything like that? Now that we do have it in moles, we can now go to molecules by using Avogadro's number, which in this case, again, would mean 1 mole would be 6.022 times 10 to the 23 molecules. So continuing on with that number there, 0.705 moles of C2H6O. Once again, we want to go opposite. So moles are up on top. That means moles should go on the bottom. And Avogadro's number should go up on top. And in this case, this would be molecules we'll use as the units. The moles here will cancel. In this case, since they're both on top, we are multiplying, in this case, those 2 numbers. Using our exponent button, maybe 23. We will get 4.25 times 10 to the 23 molecules here of C2H6O. Any question on that one there? In this case, I did 2 separate calculations since we wanted an answer for both. If we were just looking for the molecules, we could just roll it all in one calculation if you wanted to. Any questions on any of that there? All right, looking then at our other one here, which is 45.5 moles of NH3. How many grams? Once again, that is a moles to gram conversion. which means that is again just the molar mass that we need for that. There is no Avogadro's number needed here, as we're not looking for any molecules or anything like that. So we do need to get the molar mass of NH3 from the periodic table to help us do that conversion. So for NH3, we have 1 nitrogen at 1401 plus 3 hydrogens at 1.008, going to give us a molar mass here for NH3 of 17. 1703. Once again, that would be how many grams there are per mole. So again, we could use that as a conversion factor. In this case, we are actually starting with moles. NH3. Again, going opposite to get rid of the moles means the moles need to go on the bottom. And the number with the grams will go up on top. The moles will cancel here, and we'll take 1703 times 45.5. Bad lighting here, but I think my calculator says 775 grams, I think, of NH3 here. Any questions on that calculation there? Question on how to use molar mass, Avogadro's number, how to calculate it. It's best not to overcomplicate it. It really is just a conversion factor. And, you're just going to get your conversion factor from the periodic table, or obviously using Avogadro's number as a conversion factor. Any questions on any of that there? Yeah. Yeah, so Avogadro's number, the 6.022 times 10 to 23, the units that go with that number can really be anything. So most often in chemistry, we'll use atoms if it is atoms. And we will remind to update this thing later, apparently here. Remind me later. Yeah. There you go. So the 6.022 times 10 to 23, it could have really any units that you want. You could technically use any units. Like I was joking with pizzas and shoes, you could use those units if you want. But for us, atoms and molecules are the two common units that you can use. And it's the same conversion, it's just the units change. So you would use atoms in a situation like we did here or previously, where it's really just like one element by itself, like when we did the gold one, for example. You would use molecules in a situation where you have a molecule or a compound like water or NH3 or even the ethanol here. That's when you would use molecules for it. So those would be the two common sort of units that you would use for Avogadro's number, but it can be any kind of unit you want. But it is always equal to 1 mole. So that's always the same. 1 mole equals that number, but the units with that number does change. Other questions? Yeah. They in this application for Avogadro's number, atoms and molecules represent the same number. So still 6.022 times 10 to 23 equals 1 mole. So basically what we're saying is, when you say like you have a dozen of something, it represents 12, right? But that 12 could be all kinds of different things, right? If I have a dozen donuts, that would be 12 donuts, right? If I had a dozen roses, that would be 12 roses. If I had a dozen shoes, that would be 12 shoes, So just like that, a dozen represents the number 12. The mole represents the number 6.022 times 10 to 23, but it could be anything really. But for our purposes, it's usually atoms or molecules. So that's sort of the same idea. Yeah. So the mole represents, Avogadro number represents what a mole is, a numerical value, but we could be talking about different things and apply it different ways. Just like, again, a dozen donuts, a dozen, balls, the golf balls, whatever it may be. Other questions? Okay. So let's take a look at another little aspect of what you can do with this, or sometimes you may be asked. Let's actually just take the same number we just used there, 32.5 grams of C2H6O. And in this case, let's say we wanted to know how many hydrogen atoms are there? So in this case, we're actually interested in just the hydrogen atoms. We're not interested in the entire thing. We just really want one sort of part of it. And you are sometimes asked that, like, what is, the one part of it? And you can actually use the formula here as like a conversion factor to help you get there, where the numbers on the bottom represent the moles of each of those elements. Obviously, nothing written there would represent 1 mole. And you could come up with actually 3 sort of relationships from this sort of formula here. You could say in 1 mole of the entire thing, there are 2 moles of just carbon. And again, that 2 would come from here. You could also say in 1 mole of the entire thing, there are 6 moles of hydrogen, and that 6 would come from here. And you could say in 1 mole of the entire thing here, there is 1 mole of oxygen, and that would come obviously from here. So you actually come up with sort of like a mole-to-mole relationship of each of the elements that are in the formula. And what that allows you really to do is to go from like the entire thing to just the specific element maybe that you're interested in. Now, in order to do this, since these are all sort of mole-to-mole relationships, and for each of these, you could write 2 conversion factors for each of these, kind of like what we've been doing, like 1 mole of the whole thing over 2 moles of carbon, or 2 moles of carbon on top over 1 mole of the whole thing. In order to use these, since these are mole-to-mole relationships, we would need to convert the grams of the entire thing into moles, so all the units cancel. So since we did that previously, I'm just going to steal the number that we did previously. So we did this step on the last one here, and the purpose of doing this step would be, again, to get them into moles so the unit all cancel out correctly. So I'm just going to steal that number. Obviously, you would do this calculation if we didn't do this problem to begin with, but I'm just going to steal that as 0.705. So the step that we did going to moles, obviously using the molar mass to do so, got us 0.705 moles of the whole thing here. So once again, here, we're not interested in the whole thing. We're just interested in the hydrogen, which means we do want to use this relationship that we got from the equation. And we're just going to do just a basic little calculation here. We're going to get rid of moles of the entire thing. So 1 mole of the entire thing would go on the bottom. And that would then tell me I have 6 moles of hydrogen. The moles of the entire thing would cancel. And if I got a number here, we'll just get a number here for a second. Give me, looks like 4.23 moles of hydrogen. So this sort of conversion factor came from the actual formula itself, using the smaller numbers as mole-to-mole relationship. Now, in my original question here, I wanted to know how many hydrogen atoms there would be. At this point, what should I do with this number? I want to get to hydrogen atoms. What is the key word there? Atoms, which means I should use Avogadro's number. So at this point, we could take our moles of just the hydrogen, use Avogadro's number to convert it into atoms. So if we did that, 4.23 moles of hydrogen, we want to get rid of the moles. So the moles will go on the bottom. And remember, a mole of anything equals 6.022 times 10 to the 23. Here we are going to use atoms for Avogadro's number because we're talking about just hydrogen by itself. And that would then get us times 6.022 to the 23. Gets us 2.55 times 10 to the 24 atoms of hydrogen. Those guys cancel. First off, any questions on that there? Now, I got an answer here because my next question is going to be, what happens if I didn't want atoms? Yeah. Let me double check one more time, just make sure. 4.23 times 6.022 exponent button and 23. I get 24. Yeah. Anybody else get 24? Yeah. So you want to make sure you put it in 4.23 multiplication button, 6.022 exponent button, no other button, and 23. Yeah. So try that. That's what you should. Yeah. Remember, when you do scientific notation, don't hit the multiplication button, don't hit the shift log or anything like that. You're just gonna punch it in that way. Yeah. 24s, yes. 24, yeah. 24. You got 20. You got 25. Try it one more time. So 4.23, right? Times 6.022 x 23. 24, yeah. 24, yeah. All right, so it should be 24. And again, these are the only buttons that you should hit. No other buttons, yeah, and you should hopefully get there. All right, now if I wanted, say, not atoms, but I wanted how many grams of hydrogen it would be. At this point, if I want to know how many grams, what should I use to get me to grams? Yeah, we use the molar mass of hydrogen, which is from the periodic table, which is our 1.008, right? So, you could be asked for not atoms, but maybe you did want grams. So you could just do the same type of conversion we did previously. We would do 1.008 grams up on top, a mole of hydrogen on the bottom. Again, those guys would cancel, and we would end up with 4.23 times 1.008. And it gets me, looks like 4.26 grams of hydrogen. So you could obviously, we did this for hydrogen. You could do it for the carbon that's there. You could do it for the oxygens there. The only difference obviously would be this part here, different sort of 1:2 or 1:1 relationship. And then obviously the molar mass here would be different as well. Question on how do you do just a single element part of it? Question on these calculations here. So what we're going to talk about next is kind of putting together the two things we've talked about so far in this chapter, which is balancing equations and basically grams to moles, moles to grams, to use the equation to figure out, how much, say, product you would produce in a reaction, how much reactants you may have started with, kind of putting these together. So let's take a look at that. That is what is referred to as sort of stoichiometry. And when we look at a balanced equation, there's a couple of ways that we could look at the coefficients. This is a 2, this obviously is a 1, and that is a 2. We could say in this case that there are 2 molecules of H2 react with 1 molecule of O2, gives us 2 molecules of H2O. The relationship that we are going to really use in these calculations is what is sometimes referred to as the mole to mole relationship. And that also just straight comes from the coefficients. We could say there are 2 moles of H2 react with 1 mole of O2 gives you 2 moles of H2O. The last one is conservation of mass. If you start with 36 grams of reactants, you'll end up with 36 grams of products, because the hydrogen on the left is the same mass as the hydrogen on the right. So we have the same amount. When we balance an equation, right, we end up with the same number of elements on both sides of the arrow. So they weigh the same on both sides. So that's the conservation mass. So this is what is referred to as the mole to mole relationship. It is what we use in stoichiometry to help us figure out things like, if we know how much reactants we started with, how much products we should make, and vice versa. If you actually know how much products that you made, you could do some calculations backwards to figure out how much reactants that you would start with. So it is all based on a balanced equation. So whenever you do a stoichiometry problem, it's got to always start with a balanced equation. Otherwise, all the calculations are going to be incorrect. So let's take a look at an equation here. So there are certain steps that we follow when we do a stoichiometry problem. And the very first thing, 100% of the time, is you need to make sure that your equation is balanced. So if you do not have a balanced equation here, you're pretty much might as well just put your pen down because it's going to be wrong in the end. This means that if you go back and you're given everything in words, you got to start with the right formulas and then balance it correctly, like we talked about balancing. The next thing that you do in an equation like this or a problem like this is you take whatever they give you and you convert it to moles. So very, very commonly what you are given are grams, and you need to convert it to moles like we just talked about using the molar mass to do so. So whatever units they give you, and they pretty much will only give you one thing in the equation. They may say, hey, you started with like 10 grams of oxygen, or you started with 20 grams of CO. Whatever they give you and whatever units they give it to you in, you got to get them into moles. And really the reason you have to get them into moles is stoichiometry is based on the mole to mole relationship. So all the units will cancel out correctly. So it's always convert to moles. And then the third step, no matter how crazy the problem looks like, is actually the stoichiometry part. It is the mole to mole relationship from the balanced equation. The last thing that you do is if you do steps 1, 2, and 3 correctly, you should always be in units of moles at this point. And at that point, you may need to take the moles and convert it to some other unit. A lot of times grams on the back end. So you'll need to use the molar mass on the back end of the calculation. But it really could be any unit. You may want to convert it to pounds or some other type of unit. But usually you'll have to do some type of conversion in there. That is pretty much your 4 basic steps for a stoichiometry problem, which is what this is. So let's talk about how we do these things. Stoichiometry is really not that bad. It really is just a conversion factor and a conversion problem. The problem is, or the difference is, instead of looking it up in a table to get the conversion factor, or look it up on the periodic table to get the conversion factor, we actually use the balance equation to get the conversion factor. And the reason that is, for example, they may say, hey, you started with this many grams of O2. How many grams of CO2 did you produce? So you need a way to go from O2 to CO2 in the calculation. And where we get that conversion is from the actual equation. So from this one equation that I have up here on the screen, we could actually write several different equalities from. So we could say, for example, that for every 2 moles of CO you toss in there, and that comes nothing more than the number that's in front of CO, you also need to toss in there 1 mole of O2, and that is the number that's in front of O2, which is no number, which represents 1. So we could say that 2 moles of CO is equal to 1 mole of O2. It is not equal to each other in terms of 2 equals 1, which clearly it doesn't. It is equal to each other in terms of, like, you need to throw that proportion of CO in with O2 to produce a certain amount of product. Like when you make cookies, right? You got to throw in a certain amount of flour, a certain amount of, butter, a certain amount of chocolate chips, right? To get a dozen cookies. Same idea here. That's what we mean by equal to each other. You got to throw in this amount of moles of each of those guys to basically produce your products on the other side. We could also say that for every 1 mole of O2 that you toss in there, you get 2 moles of CO2 out. We could also say that for every 2 moles of CO you toss in there, which is here, you get out also 2 moles of CO2. So from this one equation here, we could actually have 3 different equalities. And for each of these equalities, we could write conversion factors. We could write for the first one 2 conversion factors. we could say that there are 2 moles of CO over 1 mole of O2, or we could write the opposite. 1 mole of O2 gives us 2 moles of CO. For the second one here, we could write 2 conversion factors. We could write 1 mole of O2 over 2 moles of CO2, or we could write 2 moles of CO2 over 1 mole of O2. And for the third equality, we could write 2 more conversion factors. We could write, we'll go over here, 2 moles of CO over 2 moles of CO2, or 2 moles of CO2 over 2 moles of CO. So from this one equation, we have 3 relationships and gives us 6 different conversion factors that we could use in the process of solving a problem. Will you use all 6 conversion factors? I'm going to say no, otherwise you're doing the problem really wrong. So you're just going to choose the one that's going to work for you. But these are the 6 different conversion factors that you could actually get from this equation to help you solve whatever may be asked of you. So again, if you're using all 6 of them, you're definitely doing it wrong. Yeah, so you just need to pick one of them. So for example, in this problem here, if we had let's say get rid of these here and get a little bit more place to write here since we have our conversion factors. All right. So let's say that we started with, 25 grams of O2, and we want to know how many grams of CO2 would we actually produce. So we're going to dump into this reaction 25 grams of O2, and we want to see basically how many grams of the CO2 we should produce. So if we follow our steps here, this first step is to make sure our equation is balanced. So we're good. We do have obviously our equation that's balanced. The next thing that we want to do is take whatever they gave us and convert it to moles. Do I need to do that in this case? That is 25 grams of O2. Do I need to convert that to moles? I do. It's not in moles, right? So that is grams that need to be converted to moles. So to convert grams to moles, I need the molar mass of O2 in this case, right? From the periodic table like we were just doing. So oxygen is 16. So the molar mass of O2 would be 2 times 16, and that comes from the periodic table. And that's a 32 grams per mole. So the very second step that I'm going to do in my calculation is take the grams that they gave me, and I'm going to use the molar mass from the periodic table like we were just doing in those calculations, and I'm going to convert them into moles. So if I do that here, I will end up with 25 divided by 32. Gives me 0.78125. I'm not going to round just yet. Moles of O2. So that is basically the second step that you do in these problems. Whatever unit is given to you in, you need to get moles. That also means that if they give it to you in moles, what do? You just go on to the next step. Don't unconvert it. Sometimes people want to unconvert it out of moles and then reconvert it back. So if it happens to be in moles, you're good to go. You just kind of skip that step and go to the next step. But if it's not in moles, you got to get it to moles. And that in a lot of cases will be 1 calculation, maybe 2 calculations, hopefully not a lot of calculations, but you may have to do multiple kind of calculations to moles. But at some point, you should be using the molar mass at the end of that journey to get you to moles. Now, my problem here is I am stuck at O2, right? But I'm not really interested in O2. I am interested in CO2. And this is the third step in the big stoichiometry part of it. This is where we go to the equation like we did previously, and we look at the two things we're interested in. One thing we're interested in is what they gave us, which was O2. The other thing we're interested in is what we are looking to find, which is the CO2. And that is where we use the coefficients there to find our mole to mole relationship. And that is where we saw earlier that 1 mole of O2 gave us 2 moles of CO2. That is what we're going to use to basically just change the units from O2 to CO2 in this particular example. From that equality, we had 2 conversion factors, which happens to be right here in the middle, which is good. So this is the point where we're not going to use all 6 of them that we wrote. We're actually just going to use one of the 2 here that makes sense based on the calculation that we're doing. So what one makes sense here when we come to our third step? Well, in our third step, we're going to start with 0.78125 moles of O2. Which one, what do I want to get rid of here? I want to get rid of O2, right? And I want to be left with CO2. Do I use the conversion factor on the left to do that or the one on the right to do that? I am going to use the one on the right. It is opposites cancel. So this is the only conversion factor that I'm going to use here in this problem. And that's going to go with 2 moles of CO2 up on top and 1 mole of O2 on the bottom. That is going to cancel the O2. And this is the big stoichiometry part. And again, that comes from nothing more than the actual numbers that are in the balance equation. There's no calculation to figure out those numbers. It is literally just the numbers that are in front of everybody in the equation. And if I do that there, times that by 2, it's going to give me something. Looks like 1.5625 moles of CO2. So that third step is really important. That third step is the stoichiometry part. And the only way you could do the third step correctly is to do the second step, which is to get it to moles so everything cancels out correctly. Any questions so far? If all I wanted to know was how many moles of CO2 I would produce, I could just put a box on it, right? I'm done. That would be the calculation, clean up some sig figs. But in this case, I actually don't want moles of CO2. I want grams. So I am now going to be going from moles back to grams. So what do I use to go from moles back to grams? It's hanging on the wall. The periodic table and the molar mass. So we're going to use the molar mass to go back from moles to grams. But it's important at this point, I am no longer doing O2, right? I am doing CO2. So I need to get the molar mass here now of CO2. So again, we need to go back to the periodic table and get the molar mass of CO2 because that is basically what the stoichiometry got us to. So that would be 12.01 grams per mole for our carbon plus 2 times 16 for our oxygen. Going to give us 44.01 grams per mole as the molar mass. So the last step here, which a lot of times you do need to do, which is the fourth step, we're going to take our moles of our product in this case. We're going to use the molar mass like we did in previous calculations. We want the moles to go away. So moles of CO2 on the bottom, the grams up on top from the periodic table. The moles will cancel, and that's going to get us about 68 point, we'll call it 69 grams actually. So we'll call it 69 grams here of CO2. Significant figure wise was based off the 25 grams, which was the only number we had really given to us, which was 2. So we ended up with 2. Every single stoichiometry problem is pretty much the same 4 steps. Just follow it in order and it will get you to the end. What this really means is if we did this reaction and we tossed in there 25 grams of O2, everything went perfect. You weren't a klutz and spilled anything. There was no side reactions that occurred. You should, in theory, make 69 grams of CO2. That is what is sometimes referred to as the theoretical yield. That is actually what should come out in that reaction if everything went perfect. Things don't go so perfect a lot of times, but that is technically what it should be. Any questions on any of that there? All right, so let us take a look here, maybe at one more here. Sort of talked about that there. All right, so why don't you try this one here? Let's do lithium metal reacts with water. So we'll do lithium, we'll give you the equation here, plus some water, make some lithium hydroxide and H2, I think. All right, so why don't you try this? We're starting here. In this case, we want to know how many moles of H2 will you produce if you start with 5.32 moles of lithium. So follow the 4 steps. First step, balance equation. Second step, convert to moles. Third step, mole to mole relationship. Fourth step, convert moles to some other unit. All right, so give it a go. See what you come up with here. So since we're getting to the end here, let's take a look together and see how you're progressing. So again, you always just want to follow these 4 steps. So the first one is we want to balance the equation. It is not balanced. You do need to lay up, I think, a 2 there, perhaps a 2 there, perhaps a 2 there, perhaps no 2 there. And I think that will make it balanced at that point. The next thing that we want to do is simply take whatever they gave us, which in this case is 5.32 moles of lithium, and we want to convert it into moles. Do I need to do that in this case? I do not. It's a little check mark, and now I'm going to move on to the next part of it, which is the stoichiometry part in this case. So they did give us lithium, which is here, but we're not really interested in lithium. In the end, we want to know how many moles of H2, which is over here. So this is where the stoichiometry part comes into play. We're going to go to the equation, and all we're going to simply do is look at the coefficients in front of each of those. And in front of the lithium, it says 2, so that means there's 2 moles of lithium. In front of the hydrogen, there's nothing written, which means there's 1 mole of hydrogen. That's going to give us our 2 conversion factors that we could use in this problem, which would be 2 moles of lithium over 1 mole of hydrogen. Or you could do the opposite, 1 mole of hydrogen over 2 moles of lithium. So we're going to do our second step, our third step here, actually. And which conversion factor should I use in this case? The one on the left or the one on the right? It is the one on the right. We want to get rid of lithium, so it needs to end up in the opposite location. So since lithium's up on top, the 2 moles of lithium on the bottom, the 1 mole of hydrogen up on top, that is from the balance equation, just the coefficients, and that's the stoichiometry part. So the moles of lithium here will cancel. We're essentially taking 5.32 and we're dividing it by 2, right? Is basically what's on the bottom. That gives me 2.66 moles of hydrogen in this case. That is step number 3. Step number 4 is to take moles and convert it to some other unit. Do I need to do that in this case? I am looking for what for my answer? Moles of hydrogen, which means I put a box. And I am done, right? If I did want to convert it to grams, what would I need to do that with? I would need the molar mass of H2, right? Which if you go to the periodic table, did not ask you to do it in this problem, would be 2 times 1.008 grams, right? Per mole, basically 2.016. And if we did want it out of curiosity, it would be something like 5.36 grams of hydrogen, but we weren't really asked for it. We could stop at that point. And sometimes you don't need to do the fourth step, but a lot of times you do need to do it. In this particular case, we didn't need to do it. But it is just the same 4 steps. Step 1, balance the equation. Step 2, convert to moles. Step 3, and in this case, we really didn't need step 4 to do it. So it's really just those same steps. Any questions on that there? All right, we were laid up there for today.